Welcome to my talk about clean test, my modern testing framework. So since this is my first conference appearance, maybe a few words about myself. I'm Philipp. I actually did a PhD in mathematics and worked on algorithms that optimize the physical layout of computer chips. And after that, I joined DeepL. DeepL is an interesting European startup that develops neural networks to help people work with language. And we have a fast-growing user base, which brings both challenging algorithmic and technical problems. And some of these we solve with C++ services of our own that benefit from the latest tooling and C++ standards that is out there. So if any of this sounds interesting to you, we have many open engineering positions, several of which are in C++ teams. And yeah, you can take a look at our page or talk to me. But back to my talk. So clean test is the testing framework that I wish existed a couple of years ago. And here's my attempt to bring what I wish a testing framework offers. So it's standard, written in standard C++, and does not use any macros. So nowadays, if you execute tests sequentially, you essentially waste resources, both your time and your machine's time. And this is why clean test executes tests in parallel and supports simultaneous failures of assertions. It is not header only, because that would mean that every user is going to recompile the framework in every translation unit, but instead it's almost as easy to integrate. It's a CMake library that does not have external dependencies. And it has all the expected convenience functionality for USCI pipelines. For instance, it can export Junit reports of your test runs, and it can deal with invalid Unicode. And it's released under Boost license, so very liberal. On the right, you see the first example, and you might already notice that you don't need to bring your own main function. You can, of course, bring your own main function, but as in this case, you don't have to. And what I want to point out, so since this is just standard C++, you can, even without continuing to listen to this talk, take this demo and discover clean test on your own. So for instance, expect is a function, and you can take your favorite IDE and start to poke around in this example, read the documentation, and get an understanding how the framework works and how you are supposed to be using it. But nevertheless, I of course want to take the opportunity and explain the three basic concepts that you already see here, which are concepts, which are suits, tests, and expectations. So first, this QR code leads to the presentation PDF in case you want to have clickable links. So this slide is here for a second, so you can take a copy if you want. But of course, the PDF will not go away. So let me start with a test suit. A test suit is something that is a callable object that is executed automatically upon program start. So when you execute your test binary, these suits are invoked. And they are, of course, they are just some callable object, and you can do whatever you want in that, but you are supposed to be setting up tests inside suits. And the primary reason why it's handy to set up tests inside suits is that suits set up the right naming scheme. For instance, in this case, we have a talk suit, and this talk prefix will be used by all the tests that will be defined inside this talk suit. And of course, suits nest. You can take a couple of suits and start to build a tree of tests. A test case, on the other hand, is something that is executed later. So notice not all tests will be executed all the time. Some you can enable and disable some of them, and some will just be skipped. And and a test case is something that is supposed to be standalone, and you need to be careful that you don't, I don't know, capture, have a dangling reference in the capture, for instance, but these are standard problems with C++. And I would just want to point to the special assignment that I have to use in line 7. So this is necessary on namespace scope, so there's no way around that. But otherwise, I always use the syntax that I prefer most, which is with these user-defined literals and the assignment. In case you don't like this, you can, of course, stick to ordinary constructors and objects, which I do in the second example. And you can either assign into a test or suit, or you can use the respective callable object as a secondary constructor parameter. And a test does not only have a name, which is basically just a string, but it also can be tagged. And these tags, so in this case, I tag the third test case, and these tags can then be used as additional criteria to enable or disable tests. And so now let's see how this looks if you run it. On the left, you see how this test binary works if you just run it without extra parameters. First, see that the test cases are indeed executed in parallel. So you see that a bunch. So basically, we start 3 test cases before any of them succeeds. So before any of those is done. Of course, then now I want to emphasize that this is not like a possible output. Of course, it's non-deterministic, but it is so the process of building this PDF actually includes compiling the demos and capturing the real output I got yesterday evening. And so this in particular means that all the demos that you will see today really compile, and this is the output that I got. On the right, you see that what you can also do with this test binary, you can use --list, which instead of executing the tests, prints this nice Unicode tree of what's inside of this executable. And there you see the 3 test cases, some of which are tagged. And then you can start, for instance, to write a filter that selects parts of the branches of this tree that you are maybe interested in, and after that you omit the --list and execute your selection. In addition, there are many other runtime parameters that you can play around with, but you can, of course, discover these on your own using --help. And that brings me to the third and probably most important concept of clean test, which are expectations. And so for this, as you already saw, we have the expect function, and it is, for instance, in line 7, so this is the first expectation that is succeeding, so on the corresponding console output on the right, you don't see an error. And on line 8, we have the first failure, and you see that we correctly capture the line number and report that something is wrong there. But what's certainly unsatisfying is that we just print the value false. What we would have liked to see would be that on the command line, we see where this false is actually coming from, why the expectation is violated, and which values correspond to this violation. And so the sad truth is there is no way to get this without macros on this level, because essentially whatever we pass into expect is already converted to a bool, and so expect has no way of finding out where this value of false is coming from. For expect, it's simply a bool with false. But of course, there are solutions for that, and they require a little assistance of the user. And the essential idea is that we will not be passing the Boolean value to expect, but instead, we will pass an object that is basically the expression tree. So the tree of how your expression looks like. And to start building this tree, you usually start by another API of clean test, which is called lift. And lift wraps wraps a given argument into a thin wrapper. You will see details in a second. And the wrapped objects then have overloaded operators to start to build this kind of expression tree. And how that can look like, you see, for instance, on line 9, where, of course, all these assertions are failing because we want to see the failure message. And on the right, you see that it is indeed working, that we can lift a pointer and compare it to the null pointer and get like the real addresses that have been compared on the command line. And for convenience, again, there are many user-defined literals, again, that work on scalar or string types that you can use to lift these values. And so the 7_i in line 10 is a lifted integer of value 7. Okay, and yeah, so this is probably the core feature of clean test. And therefore, I want to spend some time to explain how this is really working in detail. And after that, I'll come back to a bunch of higher level features of clean tests that are also built in. And so this whole idea to pass an expression tree along is, of course, not new. I didn't know the name, but of course, I didn't certainly not think that I would be inventing it. But it's called expression templates, and it's apparently already known for more than 2 decades, which at least surprised me. Yeah, so now we'll go through a first demo implementation. Of course, it's not the real implementation, but it's roughly accurate, and we'll see how that works. So I want to explain the example that you just seen, so how lifting and equality comparison works. So let's start with a clause. A clause is the result of lifting something. So that means the clause is the thin wrapper that I just announced. And since it's wrapping something, we have a template argument, and the constructor just forwards into the cached value, so to say. And then a clause provides three functions as an API, and all expression objects that clean test will be dealing with have the same API. And so let's go through each one of those. So the first one is value. Value means get me the value of evaluating the tree that is below you. So in that case, it's very trivial because a clause is a cached value, and so the value is simply this object. Then we have a conversion operator to bool, which is necessary for using clauses and other expressions in static asserts. The implementation is always the same, like in this line 22. And the third one is the output operator. The output operator is supposed to print not what the value is, but instead how the value has been computed. So for this first example of the clause, this is the same. That's why line 27 simply prints the value, but you will see more interesting examples in a minute. And then we have the expression concept in line 32, which identifies all of the expression objects that that come from clean test as being those which derive from tag. And then with that, we can go through the implementation of lift. So lift gets anything, and then does a case distinction. Either the given object is already some expression, then we simply forward, we are the identity function, and otherwise we wrap the given argument in a clause. So pretty simple. Let's look at a more interesting example, equality comparison. It works pretty similar, so now we have an equal object. The equal object will be the return type of an equality comparison of 2 expressions. That's why it has 2 template parameters, both of which, again, are already expressions. So then the constructor simply forwards into both left and right-hand side. And then we have to go through the 3-level API again, which in this case is a bit more interesting. The value is the equality comparison, of course, of both left and right-hand side. But since the left and right-hand sides are themselves expressions, we have to ask for the value in order to, to get the right objects to compare. That's line 57. Operator bool is standard as always. And then the output operator now is a bit more interesting because now we don't print the value anymore, but instead we print the both left and right-hand side that has contributed to the evaluation. Again, so the left and right-hand side are expressions, and so line 66 and 67 again use the output operators of those expression objects. And with that, we can overload the equality operator. We take a left and a right-hand side, and then for convenience, we just lift both of them, because we know if this is already an expression, lift is doing the right thing, and then we just build an equal object around it, which with the deduction guide above does the right thing. Notice that, so in this example, I omitted the necessary concept requirements for this operator. So you, on the one hand, you should check that at least one of left and right-hand side actually is an expression, because otherwise this operator should not take part in overload resolution. And the second thing is that you should also check that the underlying values of left and right-hand side are in fact equality comparable, because otherwise this is not going to work anyways. And so clean test does this, but I'll omitted this for this mock-up implementation. So the last remaining ingredient is demo of expect. Of course, so the real expect of clean test does some bookkeeping, which I entirely skipped. So this is, but it's sufficient to understand the core aspects of expect. We take something, and then we print whether this expectation was met or not. So we need to convert it to bool, and we just print some tag for it. And also we print t, which, if in case t is some expression, has a chance of printing the expression tree. And so this works pretty well. Line in 95 demonstrates that it even works at compile time. And line 96 shows that it also works to print this simple equality comparison of 7 and 8. So at that point, you might wonder or have a sense that lines 88 and 89 could be considered a code smell, because we might be calling the values multiple times of t. And so you are correct with that. It's actually a real problem, and in a second you'll see why. We come back to that. Yeah, and before I want to, let's say, introduce this tree notation. So this is basically the expression tree, and it is rooted at the equality operator, the orange box, and it has two children, the clauses, the yellow boxes of the lifted values 7 and 8. Okay, so that's pretty trivial, but we come back to this notation later, and there it will be helpful. Okay, so this is equality comparison. So, of course, when you write expectations, you don't only want to equality compare values, and therefore clean test overloads not only equality comparison, but 22 operators in total. So these are unary operators, arithmetic operators, bitwise operators, comparison operators, and even special operators like comma, and or. First, I personally prefer the textual version of not, and or, so don't get confused. So it's equivalent to, of course, the exclamation mark, double ampersand, and double bar. Second is, all these, of course, C++ even has more operators than these, but those are the ones that usually operate on constant arguments. And so that's why I only overload those, because otherwise it's probably very confusing whether the printed value would be the one that was taken before applying the operation or after. So in either case, you probably confuse half of your users, which so therefore I just don't do it. So and yes, so then among all these operators, the implementation for and or is the hardest one to get right, and that's why I also want to present that one. So we will start with the first attempt, how you could implement it, and see how far we can get. So this is the attempt. In essence, it's pretty much the same as equal that you've seen 2 slides ago. Or is a binary operation that takes 2 expressions, the constructor of just 4 words, and now it's a copy of the equal object with 2 modifications. The first modification is in line 103, where, of course, instead of applying equality comparison, we apply the or of left and right-hand side value. And the other difference is in line 113, where we switch out the equality comparison string for the or string. So pretty simple. And we can use it. And so with an or, you can do for instance, you can use an or to get these pointer checks that you are used to. And these standard pointer checks follow along the lines that you either want the pointer to be null, or you want the pointer to hold some value, in this case 42, okay. And the corresponding expression tree is shown on the bottom. And so, maybe unsurprising to some of you, this crashes. And now, it's maybe not super intricate that it is crashing, but still it's interesting to understand why actually it's crashing. And so let's understand that. So or is an operator that is special because it is supposed to have short-circuiting semantics, meaning that after evaluating the left-hand side, there's a sequence point, and you decide whether you even consider the right-hand side at all. So usually on an or, in case you do this type of check and you come with a null pointer, then you don't evaluate the right-hand side, whatever is written there. But this short-circuiting does not apply to overloaded operator ors, which is due to the fact that basically an overloaded or is a function that takes 2 arguments, and if you want to call that function, you need to bring both arguments. So there's no way of skipping evaluating the right-hand side argument of an overloaded or. Okay, but still, how do we actually crash? So we do not crash in line 103 because line 103 applies an or to after getting the respective values. So in this case, the values are bools. So the or in line 103 is in fact short-circuiting. So and it is correctly only evaluating the left-hand side and skipping evaluating the right-hand side. But of course, line 113 does indeed crash because we are unconditionally evaluating the right-hand side, or upon printing it. In an attempt to print it, I should rather say. Okay, so that means we should probably fix this print. There are 2 options how we could fix it. One is we just re-evaluate the left-hand side to see whether we are supposed to print the right-hand side. Sorry. But that could be costly. I mean, there are examples that you can come up with where it's even impossible to re-evaluate the part of the tree that you had before. And so this is not the way we are going. Instead, we will add caching. So let's attempt to add caching. So first, for that, we need a template alias. This template alias is yeah, sure.
Why are we crashing on 113? We are only printing it, and printing it should not evaluate it.
Yeah, of course. Yeah, but you want to. Yeah, I mean, you usually when you print the star, so the star is probably a bit special because it's not too useful to simply print the address and say, yeah, the value can be obtained by, or could have been obtained by printing whatever is inside this address, but usually you also include what is lying there, and that's what I also do here, because otherwise it's less useful. So yeah, but that is a true remark.
But you should not try to print it if it's a null pointer, should you?
Yeah, of course, you can also add a check there, but I mean, you are not supposed to be going down this path anyways. So, yeah. Okay. So again, let's try to fix it by adding this caching layer. So it could look like this. We start by introducing a value template alias, which determines the type that is returned by the value of call on some given expression. And with that, we have this caching OR that replaces the former OR. It has, again, a left and right-hand side expression, and in addition, a cached left-hand side value, and optionally also a cached right-hand side value. And then we, in the constructor, after forwarding left and right-hand side, we cache the value of the left-hand side, and then depending on whether it is true or not, or true-ish or not, we either skip evaluating the right-hand side, or we do evaluate it. And then, again, line 114 in the value call is pretty similar to the thing that we saw before. Notice that we don't need to check whether the right-hand side is available, because in the constructor we ensure that it is available when we need it, essentially. And then in the output operator, we add this conditional print that either prints the right-hand side or prints an unknown string to indicate that we did not pursue this expression tree in that direction. Okay, and so that fixes this example. So in that case, we correctly, let's say, print that we did not consider to evaluate the right-hand side branch of the OR. The problem, though, you probably have guessed it, is that there is another example. So the problem is that, so this is a different example now. The corresponding trees are on the right, and the ORs have line numbers in the bottom, and they correspond to the line numbers in the code. And so I'll go through the second example. So that is again an expression that is rooted at an OR, and it has two children. One of them being the not P check that you've seen before, and the other one is again an OR, which checks that P dereferences to not a non-zero value or false, which doesn't matter. So the thing here is that, again, evaluating the left-hand side branch of this OR in line 193 is again crashing, because it involves dereferencing the null pointer. And so, but that is precisely what we implemented one slide ago in this caching OR implementation. So, or in other words, so in case our OR is part of an unevaluated tree of the expression, branch of the expression, sorry, we should not even consider evaluating its left branch. Okay, so we need to fix that. What we can do is we can try to use mutable data members to also wrap the left-hand side value in an optional and only initialize it upon the first value call. Problem, though, is that these mutable data members are not available in constexpr context. And so, to be honest, so this is where I arrived at some point, very in the beginning of clean test, and it really seemed like a dead end to me. So I did not, for some days, know how to solve that. But I decided, so either I can find a way to get this working, so then I will implement all these 22 operators and everything else that is missing, or I will probably abandon this project. And in the end, of course, I solved it, and I'll show you how. And it comes pretty much down to the fundamental theorem of software engineering. And so we will be adding another level of indirection. And so now we will have 2 layers. One is the expression layer, which is constructed eagerly, that builds the expression tree. And the other layer is a sort of evaluation tree, if you want, and that is only constructed lazily, where it's actually relevant. And so let's see how that looks like. So this is the final implementation, that will actually work. So now we have the OR expression, which again has 2 operands, but does not cache any values. And we notice that we now change the API. So an OR now simply has an evaluation function, which returns an evaluation object of this OR that is constructed from this OR. And you will see on the next slide how such an evaluation object looks like. And other than that, this OR expression only provides the conversion to bool for static asserts again. And there you already see that an evaluation happens to bring now this value API that you've seen before. Okay. And now let's look how this evaluation object looks like. The evaluation object has has 2 template parameters. Notice that the template parameters now are not the expressions anymore, but they are the evaluations of the respective left and right-hand side expressions. And then we have a left-hand side evaluation, a right-hand side evaluation, which is wrapped in an optional, and also a cached value. And then let's go through the constructor. It accepts some expression, which is an OR. So it's the OR that you've seen before. And then after initializing the left-hand side evaluation in line 145, we conditionally also initialize the right-hand side evaluation if it is necessary, so in case value is false-ish. And then we also cache the value of the entire OR. Okay, so that makes the implementation of the value API very simple, because it's line 161. We simply have used the cached value. And upon printing, we have all the details that we need. We either print the left-hand side, we always print the left-hand side evaluation, and then depending on whether we have the right-hand side, we also include it. Okay, so, and this really fixes also the third example that I provided. And to visualize it, on the right, you see now the corresponding expression trees, and with their respective evaluation trees. These are now the blue trees. And there you see how that would be constructed on these examples. And now you see that we really support the case where neither of the OR branches in line 193 are evaluated, because we skip entirely constructing this evaluation object. Okay, so now let's, okay, of course. So we changed the API of the OR expression object and basically split it into the expression and the evaluation. And of course, that needs to be carried over to every other operator of the 22 that I announced. And that is, of course, done. And most of the boilerplate is hidden behind a CRTP base, but still, it's work that needs to be done. And of course, that I should have mentioned that you see the expect function again, which also needs to be adapted. So we need to query the evaluation once, and then both convert this object to bool and print it. Okay. And so now let's go back and ask ourselves, so what does this mean for a user of CleanTest? So one is, if you want to have this sort of perfect expression introspection, then you need to make sure that every operator of your expectation is applied to at least one expression of clean test. So usually that means apply lift somewhere. But you should not be scared too much. In case you do this incorrectly, the worst thing that could happen is that the command line output is not perfect, but still you will capture errors reliably, and you maybe fix the output later. The other thing is that all this, the entire idea sort of stops at function calls. So take, for instance, line 16. So you again check that this P is is either 0 or we dereference it. And if this dereference operation, for instance, is done inside a function or on, as a parameter to a function, then this works on the standard OR, so to say, line 18. So you expect that this is working. But of course, it is not working if the left-hand side is a lifted object or an expression of clean test, and the OR in line 18 is the overloaded OR, because then again, you don't have this short-circuiting guarantee by default. And so this would evaluate the right-hand side and, of course, crash. So there are two alternatives to get that. One is you can spell out this conditional check more explicitly, like I did in line 2222. The other alternative is that you can also lift the function invocation, which is another case that the implementation of lift actually provides. So you can to lift, you can bring a callable object, and then the return thing is a lazy function call, meaning that clean test will use the given callable object when it's necessary, and otherwise the object will not be invoked at all. And so in this case, we can fix it by wrapping this use dereference P in a lambda and lift it. Okay. Okay, so this is about the machinery behind expect. And so now I want to get back to more high-level convenience features of that clean test is also bringing. The first one is you can add debug output. Okay, that can be pretty handy. For instance, in case you have additional data that is useful for debugging, and you want to include it in case of an error. And again, you see on the right how that would look like. The other thing is, so usually if you have a test case with an expectation, and the expectation is failing, then the execution of the test case continues even after the failure. But of course, you remember that the test case was a failure. Instead, you can also you can get stricter expectations by marking them as asserted. In that case, when you hit a failure in an asserted expectation, then this will abandon the entire test case. So in particular, then it is the potentially dangerous code that follows after it will be skipped. And quite the opposite is that you can also mark expectations as being flaky, meaning that the failure will be recorded, but it will not cause a failure of the corresponding test case. So the execution goes on, and the test case will be considered a pass, even though you saw an error on a flaky expectation. And both of them, both flaky and asserted expectations can also be introduced conditionally. You can also check for exceptions with the throws API. You can either check for any exception being thrown or for an exception of a certain type. In that case, in the example case, we only want to see whether the given object can be invoked without an exception, and that, of course, can simply be done by negating it. So what throws is returning is essentially a bool that nicely prints to the command line. And you can also check for harder types of failures. You can check for aborts or aborts in debug mode, which is handy in case you are using assert. The only caveat is that this is not supported on Windows currently. The other thing that you might want to use in expectations is comparison of numbers. And so, in particular, of course, floating point numbers. So, let's say you have two doubles, let's say line 19 and 20, two results of adding doubles. And of course, this is a deliberately chosen example, so that is mathematically, both numbers are the same. But if you compare the doubles, then you get a failure, line 22, or console, and you see it on the console lines 3 and 4 on the bottom. And what you usually do with doubles is you don't check for equality, but instead you check for closeness. And so CleanTest is bringing this isClose API, which takes two arguments, and then in that case identifies those x and y as being close. What you so isClose is just a shorthand, and what it is a shorthand for, you can see in the resulting from the failure in line 24. I artificially changed the right-hand side of this expression significantly, and as you can see, isClose is on console lines 6 and 7. isClose is computing both the absolute and relative distance of these values and comparing it to some default tolerance, which is by default are the epsilon values of the respective value t that is used in this expression. And so the absolute and relative distance are computed using a norm. More specifically are the CleanTest utils norm, which is a customization point object that that first is constexpr and returning t in cases where stud norm, which got introduced with complex, is only returning double. So that's one difference. The other is that it's extensible by either ADL or member functions of your custom types that you might be working on. And yeah, but of course, so isClose is just a convenience shorthand that is likely useful in many cases, but in case you need something different, then of course you can spell this out yourself. You can, that's what I do in line 27. You can come and take the exact same expression that was failed in 24 and compare it to some tolerance where we artificially increase the absolute tolerance, and then this expectation is met again. Okay. Okay. At that point, you might be wondering, okay, so this sounds pretty nice, but I happen to be stuck with some other testing framework, and it appears to be very tedious to go basically through every line of my test code and start to apply this lifting logic. And I can offer some help. So I also have an accompanying project, which is CleanTest migration. It's implemented in Python. It's just started as I thought it was a quick and easy way to get this migration scripts. Turned out it was actually quite some work and way more complicated than I anticipated. So these converters are not a compiler, and therefore they are only a heuristic that is tuned and works well in practice. On the bottom, you see how that works for a sample boost test case translation unit. And so what these migration tools do is they take your expectations, they really build this expression tree, and then decide which of the nodes need to be lifted in a way that, on the one hand, brings this sort of perfect expression introspection, and on the other hand, requires to lift as few nodes as possible. And yeah, you can and then, of course, you need to, in addition, you need to switch out a bunch of macro calls with the respective clean test construct. And in that example, it works flawlessly. So I should point out that this macro switch is I currently only implemented for Boost because that was the most pressing concern for me at that time. But of course, it can be extended to other frameworks. And you should not expect that these tools work perfectly in all cases. For instance, macro-based frameworks differ significantly to clean test for obvious reasons. And for instance, it's both testing frameworks have different allow, for instance, helper functions in different places. And so it might be that the converted result needs some manual adaptations for it to make it compile. But still, it should be extremely helpful to migrate away all the tedious parts of this kind of refactoring if you want to start using clean test. Yeah, and with that, I want to come back to two even higher level features of clean test. So the first one is concurrency. So maybe one step back. So why is it that basically every unit testing framework that is out there is executing tests sequentially? The probably primary reason for that is that it makes the correlation very easy, that if you see some failure, that you always know which test case just failed. Because, I mean, you just execute at most one, so if any test case is supposed to fail, it's that one. That is different for clean test. So clean test is executing multiple test cases at the same time and needs some explicit link of an potentially failing expectation to the corresponding test case. And this is handled explicitly by a so-called observer class. So first takeaway should be that you don't need to worry about these observers if your test is single-threaded. And so all the test cases that I've shown so far were single-threaded, and so you didn't need to bother to handle any observers. And that works. The reason why it's working is that when clean test starts to execute a test case, it populates a thread local variable with the right observer. And this observer is picked up again by expect by default. So if you don't pass it explicitly, expect is using the thread local one. But of course, there are scenarios where this is not sufficient, and then you can start to bring the observer in explicitly. So on the right, you see an example how that can look like. First, the way to get the right observer is by accepting an extra observer reference argument in your test case, line 22. Notice that an observer is intentionally only forward declared, so you cannot do anything with an observer other than pass it to other APIs of clean test. And then let's go through some examples. Line 23 is picking up the default observer, so that is fine in this sort of main thread. Line 24 is also okay. That's how you bring an explicit observer to an expectation. And then, but let's see what happens if we do something in another thread. So async is a function that just calls something in a different thread and waits for the result. And so in that case, line 26, we have to use the right observer explicitly to expect something. Otherwise, line 27, so this will produce a warning on the bottom. Notice that the warning will be printed regardless of the evaluation result. So even if the expectation is met, you still get the warning, but of course you only get the warning for code that you are executing. And so line 26 basically is one possible fix for this case. The other is that you can explicitly repopulate the thread local variable by a scoped object, which is called observation setup. So that in line 30, we build this scoped object, and as long as it is alive, we can use expect as before. So given, depending on your circumstances, it might be beneficial to set this object up once and then have a bunch of expect calls after it. And at that point, I really want to emphasize that all these concurrent considerations really make sense, because expect indeed is thread safe. Otherwise, all that would not make any sense. And so you can have multiple threads executing the same expectations on the same line even, and all of the possible failures will be recorded reliably and also reported correctly to the command line. Okay, and this is the final feature that I want to touch on, data-driven tests. So I personally quite like data-driven tests because I find that these are a very convenient way of ensuring some invariance of my code by simply executing a function on different inputs. Okay. A data-driven test is a test case so that operates on a bunch of value data samples. And the way to get this sample is by accepting an additional parameter for this data sample. So for instance, line 23, the int const n. And you can pass the data in two ways. Either you use an extra constructor parameter in line 23, or you can also use the more fancy pipe notation in line 28. You pipe the data into a test. You can either, this correctly prolongs the lifetime of temporary data samples in case it is necessary. And I should also emphasize that it does not only work for homogeneous data, meaning data of the same type but only different values, but it also works for data that is inhomogeneous, so maybe a tuple of different types. So you see an example for a vector in line 22, and also a tuple example in 27. Notice that, of course, for these, you need to make sure how you work with references. So this data is marked as static, so it has its lifetime is sufficiently long. Otherwise, that could be problematic because in 23 we invoke the constructor on an L-value reference, and in case you really want to do that on temporary data, then you should probably consider moving the data into the test constructor. And yeah, this is how you set up these data-driven tests. And on the right, you see how this executes. You see that some of the samples, in some of the samples we pass, and in some we fail. And notice also that the test case name includes the printed data sample in case that is possible. So otherwise, we just use a counter. Okay. So that is all the features that I intended to elaborate. So let me wrap up. So clean test, I presented clean test, which is my modern, versatile, and yet very simple to use testing framework. It supports short-circuiting expression introspection without requiring macros. In addition, it also brings a bunch of productivity features that you expect from a modern testing framework. And it's built for a world where tests are both executed in parallel and also simultaneously fail. This project is, of course, never done. So my primary goal for the, let's say, next couple of weeks is getting a 1.0 release, which I think I'm pretty close to. I would like to have some more documentation online. But everything that I presented today, I think is pretty ironed out and works reliably. But of course, I have a bunch of extensions in mind that I might be implementing in the future if users are interested in. And you can, I provided references where you can read all the code that I presented today, and of course, how you can reach out to me. I value any feedback, be it even just a star on GitHub. And yeah, with that, thanks for your attention, and I think I have a couple of minutes left for questions.
Hey, good talk, good testing framework, also good intentions. One question, did you consider test matchers? So it's a different style of expressing your matches. Right now, all the you print on the console is then 0 is 7, or is not 7. So it's obvious that it's failing, but when you have more complex data types, you have one side that is evaluated through complex physics simulation or whatever, and then the other side is your test data where you compare to. And depending on who writes the test, the left side is the expected value, or the right side is the expected value. And it's quite inconvenient if you don't have one test failing, but several, and you are confused and have to look up each test, what's going on there. So if they have test matches, and you have very clear expression in the code, which side is evaluated and which side is your test data compared to.
Okay, I did not consider that. Yeah, so is there more difference there? Is there, what's the difference in addition to disambiguate maybe what's left and what's the meaning of the left and right hand side? So we probably have some function that asserts some condition then, right?
Basically, this expression system works well if you have equal comparison, because then it's very clear what is not matching or what's not working on. If you have like less than or greater than, then it becomes not really that obvious. And the test matchers basically say you don't want to limit yourself to bool operators.
Yeah.
You just say, for example, I have a string, and this string has to contain a substring.
Yeah. Okay.
So, and then that's the matcher exactly.
Okay.
And the other thing is that you can write a framework where the users can write new matches for their own data types.
Okay. Okay. I got it. Okay. Got it.
Print.
Yeah, but that is possible. So, I mean, I did not consider to write, let's call it, bring more matches, for instance, for this string example. But of course, you can, users could do that. So you can have some function that the only thing that you have to do is comply with this evaluation API. And it's pretty much the same. You can come up with your own contains function that gets two strings, maybe, and then maybe the input and the required substring that you want somewhere. And yeah, then this returns an object, probably that only captures these values by reference, and upon evaluation does the real check and then prints to the. You can also then, of course, control how that is printed to the command line and include whatever is suitable to your context. Of course, that's possible. But so this is not like available currently by default. Yeah.
Thank you very much. I really like it that it doesn't take any macros. This leads to immediate use in modules. But my question is more about compile time testing. Mm-hmm. How far does your testing framework go in the realm of doing testing as much as possible at compile time? I'm shifting as much that I can in my code actually to do the testing at compile time so that it don't have to be done at runtime. I've not seen very much about how much is const eval friendly, how much is constexpr.
Yeah. Okay.
So can you please expand a little bit on that?
Yeah, sure. So I'd say that like most of this expression, so I'm thinking hard to find places where I know that it's not available at compile time, and I don't see any currently. So most of that stuff, at least probably all of it, is available at compile time. But so you could argue that the use is limited because, of course, you don't have this nice. At compile time, you cannot argue that you want nicer console output. So yeah, okay, but so that is not available. So I mean, my primary intention to make all that available at constexpr time is to sort of justify that this overhead of building these expression trees and so on is in some sense limited, because in static asserts the compiler in the end sees through all of that correctly. And so that I got. Of course, if you use it just in a static assert, then you also just get, yeah, this expectation is not met, and you need to find out why. Yeah, if you want to have a better introspection at compile time, so yeah, that's probably something that would be very nice to have, but that would be a future extension for me.
One question, test fixtures. So if you have a suite and you want to have common setup in teardown code, how do you implement that?
So test fixtures are tricky because, so at least I cannot see currently a way where you get that without, let's say, the way you are currently used to with macro-based frameworks. And yeah, so I don't see a way to conveniently write it. And so currently it would mean that you just, in the first line, construct your fixture that your tests need. Of course, then you need to prefix every method that you're using that is provided by the fixture with the respective variable name. But apart from that, that's the most convenient way of getting the fixtures, and that's also the way, for instance, the migration tools are converting fixtures of boost test to clean test. And then, of course, this will not compile. So this is another example where the migration tools are not perfect, but what you need to do should be very obvious if you end up in this situation. But if you have an idea how to get it without macros, then I'm of course happy to discuss details. Yeah, okay. Yeah. Thank you.